Okay, in this section, we're going to talk about bearing pressure, which is section 2.1.6 of the ACI 530-11 code. Now, bear with me here. There is a lot of information on this slide to start. So I'll get right ahead explaining it. I wanted to write it out to save a little bit of time. So the only check stipulated for bearing pressure is that stress shall not exceed 1/3 FM, where FM is the compressive strength of the masonry. We'll take this to be about 1.5 megapascals, calculated from some research project I'll present a little bit later on. Just note that this is commonly almost 10 megapascals, so this value is very conservative. And then this is computed over the bearing area, AB, which is stipulated further in section 1.9.5. And the premise of this section is that we can increase our bearing pressure area as long as the masonry bearing is larger than the bearing plate, which the bearing plate is the anchor in this case, at a 2-to-1 slope from the point of the load up to A2. Now we have to meet the following conditions: that AB is less than or equal to A2 square root of A2 over A1, or maxing out at 2A1. And this drawing here shows visually what I'm talking about with A1 and A2 and how the force will actually dissipate through that wall, and we can increase A1. So if you look at the standard drawings, our adjusted bearing area AB will almost always max out at 2A1, with A1 being the original area. So we can basically take AB to be the following as 2A1, which is 2 times the wall width times the length of the inclined surface of the anchor. And the wall width should always be a minimum of 30 centimeters. We'll assume that, built to standard drawing specifications, 30 centimeters at least will be bearing onto the anchor. So finally, our horizontal force, P wall, will be calculated as follows. And this will be a little more depth for the bearing check, but we'll end up reusing this P wall value in the subsequent videos. So we have 2 conditions. We have our PreFill and our PostFill condition. PreFill is before filling the ramp. We can't rely on any ramp fill to distribute the load. In this case, we'll divide the adjusted horizontal force, RS prime, equally into each wall. Remember to calculate RS prime using the dead load geometry and forces, not the total load. And we've done this in other lectures where we're distributing the loads up based on just the dead load, just the hoisting load, but the dead load being also the decking load and just the live load. And in that case, we'll take our P wall to be just RS prime over 2. So divided equally into both walls. For post-fill, after filling the ramp and finishing the abutment, this is not as simple as distributing force based on the area, ramp walls versus ramp fill, because the materials have different stiffnesses. Stiffness is a measure of resisting deflection when force is applied. So stiffer structural elements will take a larger portion of the load, and usually loading is distributed based on measured stiffness. But due to a variety of unknowns, including workmanship and air voids, we can't determine the stiffness of each material. So we can turn to density as a proxy. Say the fill density is 1900 kilograms per meter cubed, and the walls are 2100 kilograms per meter cubed. We can use our density proxy to calculate that this is about 52.5% of the load should go into the walls, and the rest of the load should go into the fill. And there's some additional studies I'll link below on concrete air voids that discuss modifications based on this stiffness, based on density. Now, these aren't perfect matches, but they do help us round our engineering judgment. So keeping that in mind, given the variability and the unknowns, we can conservatively assume 60% of the total load is distributed to the walls. And we have our equation here for P wall under total load conditions.